Non-standard. There's, I think at CCR we don't have a non-standard analysis. Sam Santos will.
Thank you. First of all, I'd like to thank the John Templeton Foundation for generously sponsoring this research. And secondly, I'll give you my take-home message. The take-home message is there is a notion of algorithm in non-standard analysis, and intuitively any object is algorithmic if it's independent of the choice of infinitesimal in its definition. With a fancy word, this is called omega invariance, but the essential idea is we can use infinitesimals, but only in such a way that the choice of infinitesimal doesn't matter, and that would be the non-standard version of algorithm. More technically, I'll define a translation between Everett Bishop's constructive analysis and some subtheory of non-standard analysis. Proof and algorithm are the building blocks of constructive analysis, and transfer and omega invariance in non-standard analysis will play that same role. Hence non-standard analysis computability and my being here. If you'll remember this, I'll already be very happy.
To understand this, we need to.
Yeah, of course. More is coming. Most results from constructive reverse math seem to translate very nicely, so we're going in the right direction. Let's take a look at the computational landscape first. As Andrei was talking about recursive mathematics, named Rus after the Russian Andrei Markov, which is essentially all the math you can do on a Turing machine, or recursive mathematics. Classical mathematics is of course class, with its distinguishing feature, the law of excluded middle, which allows us to do proof by contradiction. Brouwer, the contrarian Dutchman, was against that, and he started his own mathematics, intuitionistic math, int. The Russians have a little bit of excluded middle, namely double negation elimination, Markov's principle, not P implies P. The thing that sets recursive mathematics apart is CPF, namely there is an enumeration of all partial functions from n to n, which is, well, blatantly false classically. Intuitionism, all functions from R to R are continuous, which is also blatantly false classically. At least we agree on the Fan theorem, which is equivalent to WKL, weak-Koenig lemma, and there's a weak continuity principle there. In between all this, in the intersection, there's constructive analysis. So that's the kind of mathematics everybody can agree on. The Russian recursive people, classicists, most of us, and the intuitionists, 0.1 of us. So Bish is a constructive redevelopment of mathematics consistent with all these three. And the central notions are algorithm and proof, and this is already apparent in the definition of the logical connectives. They use the BHK interpretation, also called intuitionistic logic. For example, to state P or Q, we have to provide an algorithm that outputs either P or Q with a proof of the chosen disjunct. So it's much more constructive than the classical version. P and Q, there's a proof of P and a proof of Q. P implies Q. It's not just not P or Q. No, it's giving an algorithm that converts any proof of P to proof of Q. Not P. P implies absurdity, or 0 equals 1. Existence is also very constructive. An algorithm should yield a witness to something, and the universal quantifier is what you would expect. So I wasn't lying when I said that algorithm and proof are central. These really are the central notions of constructive analysis. And, well, I'll define Blackboard NSA, system of non-standard analysis, where transfer plays the role of proof, and algorithm plays the role of omega invariant procedure. You can think of Blackboard NSA as a non-standard version of RCA, the base theory of reverse mathematics, and well, Steve is with us here today. Non-standard versions of RCA0 have been looked at by Jerry Kiesler and Keita Yokoyama. There's three important features, namely there is no transfer principle, and transfer is one of the core things in non-standard analysis. It essentially says that the natural numbers and a non-standard extension of the natural numbers have the same properties. That's what it says. An example is the transfer principle for pi01 formulas. For any delta 0 formula, we have this formula implies that one. So, well, you can see the idea behind transfer. The properties of n are transferred to star n, and this is of course a pi01 formula, hence pi01 transfer. This is an example of a transfer principle, and we don't have this in Blackboard NSA. It's too strong. Actually gives you the Turing jump. So of course we have it for delta 0 formulas, otherwise things are trivial, but that's about it. We don't have recursive comprehension, the building stone of RCA0, but comprehension for omega invariant formulas, so formulas that don't really depend on the choice of infinitesimal. I'll give you all the technical details soon. One more important thing is that just having non-standard analysis doesn't suffice. We need levels, which I'll explain now. The usual picture of a non-standard extension is, well, we have the natural numbers, which we call finite. A lot of new stuff is added, the infinite numbers, and all this together is star n the hypernatural numbers. Now, the infinite numbers have to be split in two, in small and large numbers, say. So here we have the infinite numbers, and some initial segment is small and the rest is large. And n1 is just the natural numbers and the small numbers. Omega 1 is star n minus n1, the large infinite number. So we have finite infinite, and infinite has a little bit more structure, namely small and large. Two levels of infinity, if you like. Now, omega invariance, which is the non-standard version of algorithm or finite procedure. We take a delta 0 formula, psi nm, very simple, and an infinite number. Then we call the formula psi n omega omega invariant if psi n omega is equivalent to psi n omega prime for any choice of infinite number and any choice of natural number. So,
sorry, but what is the language for this formula?
Second order.
So we have any functions as set as usual, or only arithmetic formula, or what?
No, we will this RCA0 is second order arithmetic, so numbers and sets. Then, because it's non-standard, you have numbers, sets, non-standard numbers, non-standard sets.
So for every set we have a constant or not?
Well, in RCA0 we can only define the recursive sets, the delta 0 sets. We only have comprehension for that. So, and what I was going to say is we have comprehension for every omega invariant formula. Normally, we have in RCA0 we have comprehension for delta 01 formulas. Here, given an omega invariant formula, there's a set with the same elements. So, what I wanted to say was, well, psi n omega, of course, there's an infinite number there, but it doesn't depend on the choice of the infinite number by definition. Psi n omega is equivalent to any psi n omega prime. This is the way infinitesimals are usually used in physics. Infinitesimals don't really exist. They play around with them, the physicists, and the end result is never dependent on the choice of the infinitesimal. And for such an omega invariant formula, we can have a set with the same element, a standard set, by the way, of course. Yeah, here it says. So we'll define a translation from Bishop's constructive analysis, where proof and algorithm are central, to Blackboard NSA, which is, by the way, based on classical logic. Everything is classic, like the rest of the world. So we need to define constructive counterparts, say, of the disjunction. So, well, here we have A or B. An algorithm yields a proof of A or proof of B. This is called, this new thing is called A hyperdisjunction B. And it does this. A hyperdisjunction B says there is an omega invariant formula, psi. If psi is true, then we have A and A is in T, A satisfies transfer. Or not psi means that we have B and B satisfies transfer. So as you can see, well, indeed, instead of an algorithm that says this or that, we have an omega invariant formula that says this or that disjunct, and we don't have a proof, but we say that the formula satisfies transfer. A implies B is an algorithm converts a proof of A to a proof of B, and that's A hyperdisjunction B on this side. If we have A and A satisfies transfer, then we have B and B satisfies transfer. Again, A and T means A satisfies transfer. Here we of course have an algorithm that converts a proof. Here the algorithm is sort of implicit because we only have comprehension for omega invariant formulas. So anything we want to do in Blackboard NSA has to be omega invariant by design. Now as an example, for example, a universal formula is in T means that, well, if it holds, then it holds on all numbers. So as I said, we don't have pi 0, 1 transfer, so some pi 0, 1 formulas satisfy transfer and some don't. And this is very important. An existential formula, if that is in T, if it satisfies transfer, then it doesn't satisfy transfer fully. Here we go from the finite to the infinite, but for an existential formula we only go from the infinite to the small infinite. We don't go all the way down to the finite, we go to n1, which is the set of small finite numbers. And so transfer is asymmetric, and this has a reason, which you'll soon see. Not A and hypernegation are defined as you would expect it, and existence, of course, well, as you would expect it, an algorithm computes a witness, an omega invariant function computes a witness. So if we look at the hypernegation of a universal formula, then there is a counterexample in n1. But this is much weaker than there is a finite counterexample, just as in intuitionistic logic. Intuitionistic logic, the negation of a universal formula just means, well, it's impossible that this is true. However, existence means that we can compute a counterexample. So this is much weaker than that. And we have the same thing here. So that's the reason why you have this asymmetry in transfer. You have to, because negation and hypernegation have to satisfy the same properties. And then you can look at all the intuitionistic rules of logic, and it seems to work. But, well, you want to see how this stuff behaves in practice. I mean, in constructive math. And I'll show you that the non-constructive principles behave the same here and here. So there's most, as you've seen from the diagram, most mathematical principles are not constructive, and there's this entire cottage industry called constructive reverse math, which is essentially reverse math but with a with constructive analysis as a base theory. And you'll see that you get exactly the same picture after translation. So, well, the most obvious candidate is the law of excluded middle, which is rejected in constructive analysis. So, LPO, by the way, is limited principle of omniscience. This turns out to be equivalent to the fact that you can split the continuum in two, which Brouwer also rejected. More innocently, the monotone convergence theorem, every increasing bounded sequence converges, and a slight knockoff, the Cantor intersection theorem. So, well, let's see how this translates. Blackboard LPO is P hyperdisjunction hypernegation P. I mean, that's sort of the obvious translation. Just replace the logical connectives. And then this is equivalent to x is bigger than 0, hyperdisjunction hypernegation, x is bigger than 0. So that's nice. And there's also versions of MCT and CIT. Namely, here the monotone convergence theorem says that something converges, and this limit is computed by an algorithm. Here this limit is computed by an omega invariant procedure, obviously. And the same for the point in the intersection of the Cantor intersection theorem. Now, these are all equivalent to this pi01 transfer, which we don't have in Blackboard NSA. So the constructivists reject this, while we reject that. Slight remark, this sort of handicapped dichotomy is provable. If delta is separated away from 0, then we can decide whether x is bigger than 0 or x is smaller than delta. Pop quiz. What happens here, because I mean this is in a non-standard world, what happens if we plug in an infinitesimal? I'll get back to that later. Then there's De Morgan's law, inspirationally called LLPO. Not P and Q implies not P or not Q. Equivalent to weak separating of the continuum. X times y is 0, then one of them is 0, also equivalent to that. The world-renowned intermediate value theorem, at least in constructive circles. And well, we translate, obvious translation, and we get the same equivalences. Here again, the intermediate value is computed by an algorithm, here by an omega invariant procedure. And we also have the equivalence with WKL, Weak-Koenig lemma, one of the big 5 of reverse mathematics. And this turns out to be equivalent to the disjunctive version of transfer, which states that if a disjunction satisfies transfer, then we can decide which disjunction satisfies transfer, which is of course also not available in Blackboard NSA. So constructivists reject this, we have rejected that. And to prove these equivalences, we need some kind of axiom of the continuum, not x is bigger than 0 and x is smaller than 0, and the same thing here. This may sound trivial, but it took me weeks to figure this one out. Markov's principle, not particularly interesting, but I'll list it nonetheless. We get all the same equivalences, why not? And WLPO, which is interesting because it's law of excluded middle, and it's the characterization of the existence of a discontinuous function. Here we have the same thing, and this discontinuous function is extremely discontinuous. Namely, the jump takes place in a matter of very small infinitesimal, so it's extremely discontinuous when looked at from the real topology. So, well, we get the same equivalences again. Also, before I forget, Markov's principle is equivalent to one of the projections of pi1 transfer, which is this one. Markov's principle is equivalent to this transfer principle. If there is a small infinite number, then there is a finite number. So again, this is rejected and we don't have it. WLPO is similar. So 4 remarks. Yes. I think I said my 4 remarks. Yes. So omega invariance actually is weaker than recursive, and this has to do with Markov's principle. Markov's principle can be reformulated as, well, if it is impossible that a Turing machine holds, then it must hold. Now this is actually not a Turing machine holds, then it holds, so well, that's Markov's principle. But there is no algorithmic upper bound on the time or place where it holds, so it's rejected in constructive analysis. So Bishop's notion of algorithm is actually, it can be identical to recursive. It's slightly weaker actually. So in Blackboard NSA, we call a function a formula delta 1, but if it's hyper equivalent to a pi 0 1 and an existential formula. And well, if you want to decide a delta 0 1 formula, you will need Markov's principle, just as in recursive mathematics, by the way. So this is a first natural example of, first example of something non-omega invariant. Not a Turing machine holds, I don't know. Lots of stuff can happen if you don't have Markov's principle. I'll give you one example, which has been talked about a lot in constructive reverse math, the Fan theorem versus WKL. Classically they're equivalent. The Fan theorem is accepted in intuitionistic math. WKL is the classical contraposition and it's rejected in intuitionistic math. Well, in constructive analysis, WKL implies the Fan theorem and both are rejected. Now, in NSA, WKL has this form: a tree is infinite, hyperimplication, then it has a path. But what does this mean? Well, it means the following. T is a tree. If T is infinite and its non-standard extension, star T, is hyperinfinite, then they share a path. That's what it means. Fan, well, B is actually a bar, but bar is kind of like a tree or its complement, so we're talking about trees anyway. If a tree is infinite, then it has a path. But for example, the tree can be cut off at some infinite number. We cannot exclude that. So here we see that this is much stronger than that, because this talks about the finite and the infinite world, whereas this only talks about the finite world. So we do have that WKL implies Fan, and both are not available. So I mean, there's a lot more stuff under the constructive sun, and we get lots, essentially all the same implications. So when we look up here or there, we see the same constellation of non-constructive principles with the same relations between them. So I will argue that Bishop's notion of algorithm must be pretty close to this particular notion of omega invariance, because the non-constructive stuff behaves exactly the same. I'm not claiming that it's exactly the same, but we can't be far off the mark either. That's my claim. It's sort of the dual of the work of Erik Palmgren and Ike Moerdijk. They tried to add as much of non-standard analysis they could to constructive analysis. I take non-standard analysis as basic and try to cut out something that resembles constructive analysis, but everything is classic, like the rest of the universe. And Fucino Sensei from Kobe called this reverse engineering, reverse math. I'll skip this slide because, well, it's on a note for future work. Per Martin Löw intended his type theory as a foundation for constructive analysis. And can we capture somehow type theory using this omega invariance? I mean, this is future work, right? This is pure speculation. But I think we can, by the way. There's this new interpretation of type theory using homotopy. And homotopy is just, well, what you all know. Homotopy is a constructive transformation of a continuous transformation of one function into the next. That's a homotopy. Now, with my non-standard glasses, I see not continuous functions, but I see broken chain approximations. You just take an infinite number, omega, and using that you can build some broken chain that approximates f of x and g of x up to infinitesimals. And how do we get from one broken chain to the other? Well, we just move points by increments of 1 over omega. This is called one basic step. We can do omega basic steps, move omega points, and then we should be there. And this should be independent of the choice of omega, obviously. And then, so what is a homotopy? It's actually, I think, an omega invariant broken line transformation. And in that sense, if homotopy is basic for Martin Löw type theory, then omega invariance is basic in essentially the same way. Of course, this is speculative. Don't. I mean, I'm about to try to do this. Some philosophy, if I have one more minute. So it has been observed before that the math in physics is rather constructive or computable. For example, even Gleason's theorem can be proved in constructive analysis. Douglas Bridges, whom I don't think is with us today, did this. However, I mean, physicists never heard of constructive analysis. Usually they use informal non-standard analysis. They play around with infinitesimals, engineering too, and they love it. Certainly not epsilon delta. I mean, maybe there's 5% theoretical physicists who do, and who get really angry when you mention infinitesimals. I learned the hard way. So, I mean, how do you explain this? On one hand, we use informal non-standard analysis. On the other hand, it's very constructive. Well, in physics, end results should have physical meaning. They're trying to model reality and predict reality even after all. If something has physical meaning, it can depend on the choice of the infinite number or infinitesimal used. Because, I mean, that would be cool. You take some different infinitesimal and all of a sudden reality behaves differently. And that's not going to happen, not even in quantum mechanics. So essentially, this seemingly trivial requirement makes all their mathematics omega invariant. I also found this in a 95, I think, paper by Alain Kohn. So, I mean, that's the explanation. Why is mathematics and physics so constructive? Because nothing depends on the choice of infinitesimal. It's by design omega invariant. Omega invariant is very close to constructive algorithm. So, I think I'm gonna finish here. Thank you very much.
Yeah.
So, I mean, you're basically claiming these two theories are similar, and can you formalize whether they're the same? Like, could you do that using type theory to say that? I mean, they're really just two interpretations of the same, like.
I hope so. That's would be the ultimate goal, let's say. At the very least, I can claim that there's a part of non-standard analysis that's extremely computable or constructive, which Bishop, by the way, said it isn't. But ultimately, you would want to show that one is a model of the other. There might be slight differences. I'll tell you why. Yeah, here. Here, there's for example, weak Markov's principle is also in this intersection, but it's not provable in constructive analysis. So this Blackboard NSA lives here too, but that doesn't mean that they are exactly the same. They're very similar, let's say, but whether they're exactly the same, I don't know. The problem is also that it's hard to, I mean, it's constructive analysis is not exactly a logical system. It's a little more informal. You can formalize it in Heiting arithmetic, of course.
Sorry, what is NSA? It's a logical theory,
yes.
Or it's a class of models?
No, it's a logical theory. It's as axioms.
But for example, being non-standard, it's a predicate of the language of the theory, or
yes.
not?
A non-computable one, of course, but yeah.
But what are the axioms then?
Essentially, like take a non-standard version of RCA0, throw out recursive comprehension and add comprehension for omega invariant formulas, and that's essentially it.
But omega invariance is something model property, no?
No, I mean.
But you say that something doesn't depend on the choice of omega. But this is a model.
No, omega is an infinite number. It's not a model of.
Yeah. But still, in different models, you have different infinite numbers. So maybe something is true in one or not.
But because the independence of the infinite number, it doesn't matter. Roman Kozak asked the same question. It's a very good question. Because it doesn't depend on the choice of infinite number. So.
Okay, probably not.
Yeah, but it's a good question.
What is all this? Okay, so I don't want to. Are there any other questions? Okay.